So when we say that a service is running in the cloud, what do we actually mean? It has nothing to do with those white fluffy things in the sky. It simply means that the service is running somewhere else, either in a data center or in other remote servers that we can reach over the internet. These data centers house a large variety of machines. Different types of machines are used for different services. For example, some machines may have a local solid-state drive or SSD for increased performance, while others may rely on virtual drives mounted over the network to lower costs. Cloud providers typically offer a bunch of different service types. The ones used most by users are in the software as a service category. Software as a service, or SaaS, is when a cloud provider delivers an entire application or program to the customer. If you choose a cloud email solution like Gmail, a cloud storage solution like Dropbox, or a cloud productivity suite like Microsoft Office 365, there are only a small number of options for you to select or customize. The cloud provider manages everything related to the service for you, including deciding where it's hosted, ensuring the service has enough capacity to serve your needs, performing backups frequently and reliably, and a lot more. There's a lot of software being offered as a service by many different cloud providers or other internet companies. But of course, not all of our needs can be solved by prepackaged software. Sometimes we need to develop our own. For some of the components of our software, we might choose to use platform as a service. Platform as a service, or PaaS, is when a cloud provider offers a pre-configured platform to the customer. When we say platform here, it can be a bit confusing because there are lots of different platforms that exist under a PaaS model. Let's check out an example to understand this better. Say you need an SQL database to store some of your application's data. You could choose to host the database in your own hardware. To do this, you'd need to install an operating system on that computer and then install the SQL software on top of the chosen OS. This requires a basic understanding of all these different pieces just to get the database running. There's a bunch of things that could go wrong, and even if you can eventually solve all of them, it could take a while. Instead, you could decide to use a cloud provider that offers an SQL database as a service. That way, you can just focus on writing SQL queries and using the platform, and let the cloud provider take care of the rest. There's a bunch of different platforms offered as a service by cloud providers, but of course, they're unlikely to cover all of your needs. If you need a high level of control over the software you're running and how it interacts with other pieces in your system, you might want to choose infrastructure as a service. Infrastructure as a service, or IaaS, is when a cloud provider supplies only the bare bones computing experience. Generally, this means a virtual machine environment and any networking components needed to connect virtual machines. The cloud provider won't care what you're using the VMs for. You could use them to host a web server, a mail server, your own SQL database with your own configuration settings, or a whole lot more possibilities. Running your IT infrastructure on the cloud provider's IaaS offering is a very popular choice. And there's a lot of different providers out there, big and small, that offer a service where you can run virtual machines in their cloud. Some IaaS products include Amazon's EC2, Google Compute Engine, and Microsoft Azure Compute. Now, no matter the service model and the provider you use, when you set up cloud resources, you'll need to consider regions. A region is a geographical location containing a number of data centers. Regions contain zones, and zones can contain one or more physical data centers. If one of them fails for some reason, the others are still available, and services can be migrated without notably affecting users. Large cloud providers usually offer their services in lots of different regions around the world. Generally, the region and zone you select should be closest to your users. The farther your users are from the physical data center, the more latency they may experience. This might sound a bit strange, but imagine if you were on vacation overseas. You might notice that your bank website loads a little slower. That's why it's common practice to locate data centers close to where users actually live, work, and bank. Latency isn't the only factor to take into account when selecting a region or zone. Some organizations require their data to be stored in specific cities or countries for legal or policy reasons. And if your service uses other services as dependencies, it's a good idea to host the service physically close to its dependencies. For example, if a mail server requires a database server to send an email, it makes sense to host the database server and the mail server in the same zone. We called out earlier that QuickLabs is a service using cloud infrastructure. So what kind of cloud service does QuickLabs use? QuickLabs uses infrastructure as a service. The VMs get provisioned with just the OS, and the lab automation then deploys any additional files and software into the OS. Up next, we'll talk about how we can use the services offered by cloud providers to help us scale our applications. One of the coolest features of deploying solutions to the cloud is how easily and quickly we can scale our deployments. In a traditional IT setting, if your team needs an extra server to improve the service, you need to buy additional hardware, install the operating system and application software, and then integrate the new computer with the rest of the infrastructure. Doing all of this takes time, so it's not easy to quickly scale up or down if the service gets more or less usage. In other words, it takes a significant amount of time to modify the capacity of the deployment. In this context, capacity is how much the service can deliver. The available capacity is tied to the number and size of servers involved. We get more capacity by adding more servers or replacing them with bigger servers. The way we measure the capacity of a system depends on what the system is doing. If we're storing data, we might care about the total disk space available. If we have a web server responding to queries from external users, we might care about the number of queries that can be answered in a second, which is called queries per second, or QPS. Or maybe the total bandwidth served in an hour. And we can measure capacity in other fun ways, like the number of cat videos served in an hour, or the number of digits of pi a system can calculate. Our capacity needs can change over time. Say you're hosting an e-commerce site that needs 100 servers to meet user demands. As the service becomes more popular, demand might grow, and you'll need to increase the available capacity. Eventually, the system could need 1,000 servers to meet user demands. This capacity change is called scaling. In particular, we call it upscaling when we increase our capacity, and downscaling when we decrease it. This could happen, for example, if the demand for a product decreased, or if the system was improved to need fewer resources. Cloud providers typically have a lot of available capacity that can be used by their customers. When we choose to host our infrastructure in the cloud, we're purchasing and using some of the provider's capacity to supplement or completely replace our on-premise capacity. This lets us easily scale our service to satisfy demand. There are a couple of different ways that we can scale our service in the cloud: horizontally and vertically. To scale a deployment horizontally, we add more nodes into the pool that's part of a specific service. Say your web service is using Apache to serve web pages. By default, Apache is configured to support 150 concurrent connections. If you want to be able to serve 1,500 connections at the same time, you can deploy 10 Apache web servers and distribute the load across them. This is called horizontal scaling. You add more servers to increase your capacity. And if the traffic goes up, you could just add more servers to keep up with it. On the flip side, if you're scaling a deployment vertically, it means you're making your nodes bigger. When we say bigger here, we're talking about the resources assigned to the nodes, like memory, CPU, and disk space. For example, a database server with 100 gigabytes of disk space can store more data than with only 10 gigabytes of space. To scale this deployment, we can just add a bigger disk to the machine. And the same idea works for CPU and memory too. Say you have a caching server and you notice it's using 95% of the available memory. You can deal with that by adding more memory to the node. Depending on our deployment and our needs, we might need to scale both horizontally and vertically to scale the capacity of our service. In other words, adding more and bigger nodes to our pool. This approach to scaling isn't too different from what you'd need to do if you have your servers running on-premise. Instead of sending someone to change the physical deployment, for example, adding more physical RAM to a server or adding 10 more physical machines in a server rack, we just modify our deployment by clicking some buttons in a web UI or using a configuration management system to automate the scaling for us. The infrastructure built by the cloud provider will deploy any additional resources we need. When talking about scaling in the cloud, another aspect we need to take into account is whether the scaling is done automatically or manually. When we set our service to use automatic scaling, we're using a service offered by the cloud provider. This service uses metrics to automatically increase or decrease the capacity of the system. Say you have a system that currently has the capacity to serve 1,000 cat videos per minute. If the demand for these videos increases to 10,000 per minute, and it will, the software in charge of the automatic scaling will add resources and increase the overall capacity to meet this demand. And when the users stop watching cat videos, the automation will remove any unused resources, so the operating costs stay small. But really, who wants to stop watching cat videos? But make sure you set up reasonable quotas for your auto-scaling systems. Otherwise, that viral video of a cute cat wearing a hat might surprise you with a very uncute big bill from your cloud provider. On the flip side, using manual scaling means that changes are controlled by humans instead of software. Manual scaling has its pros and cons too. When the cloud deployment isn't very complex, it's usually easier for smaller organizations to use manual scaling practices. Say your company currently has a single mail server, and you know that you'll want to have another one in 6 months. In that case, there's no need to overcomplicate that system with an auto-scaler. You could simply add the extra server sometime along the way. The trade-off here is that without good monitoring or alerting, a system without auto-scaling technologies might suffer from unexpected increases in demand. If you're using manual scaling for a service that becomes popular and demand grows quickly, you might not be able to increase the capacity quickly enough. This can stir up lots of problems, ranging from poor performance to an actual outage. In this video, we've covered concepts that are central to any solution hosted in the cloud, like capacity and scaling. As you probably noticed, cloud technology offers a ton of benefits for an IT team, but it also can be a little intimidating. Up next, we'll go into some of the reasons why IT teams might be hesitant to migrate to the cloud and how to overcome those fears. If you've always worked in a traditional IT environment with servers that are physically owned by your company, the idea of migrating to the cloud can be pretty scary. When you're running the servers yourself, if something breaks, you can either physically walk up to the server to fix it, or SSH into it from inside the same network. You can apply a quick fix and have your users back to being productive in no time. As part of the IT team, you own the hardware, the software, the network connections, and anything in between, which lets you have a lot of control over what's going on in the whole system. In the case of cloud solutions, we need to give up some of this control to the cloud provider. We have different levels of control depending on the service model that we choose, whether that's software, platform, or infrastructure as a service. When choosing to use software as a service, we're basically giving the provider complete control of how the application runs. We have a limited amount of settings that we can change, but we don't need to worry about making the system work. This can be a great option when the software provided fulfills all of our needs, and we'd rather just focus on using the software instead. But as we called out, there's only a limited amount of applications being offered in such a prepackaged way. If we need to create our own applications, we can use platform as a service. With this option, we're in charge of the code, but we aren't in control of running the application. Or we can choose infrastructure as a service, where we can still keep a high level of control. We decide the operating system that runs on the virtual machines, the applications that are installed on it, and so on. We'll still depend on the vendor for other aspects of the deployment, like the network configuration or the service's availability. If something does break, you might need to get support from the vendor to fix the problem. So when choosing a cloud provider, it's important to know what kind of support is available and select the one that fits your needs. I know it sounds strange to give away your control over the hardware, the network, and the overall infrastructure. But personally, I find that it's pretty great to not have to worry about maintaining the machines that are running our services. It means we can treat the servers executing the workloads as a commodity instead of special snowflakes. One aspect that might make you hesitant to move to the cloud is that you don't know exactly what security measures are being put in place. So when selecting which provider to use, it's important that you check how they're keeping your instances and your data secure. There are a bunch of certifications like SOC 1, ISO 27001, and other industry-recognized credentials that you can look for to verify that your provider has invested in security. Once you're sure that your provider is taking the right security measures, it might be tempting to just leave security to the professionals and forget about it. But as cloud users, we also have a responsibility to follow reasonable security practices. Google, Amazon, Microsoft, and other cloud providers invest heavily in security research. But that won't matter if the root password of your cloud instance is password1, or the instance doesn't use a firewall. In other words, we should always use reasonable judgment to protect the machines that we deploy, whether that's on physical servers running on-premise or on virtual machines in the cloud. It's also important to keep in mind that security systems can be expensive to implement correctly. Some highly sensitive deployments might warrant specialized security procedures like multi-factor authentication, encrypted file systems, or public key cryptography. But these processes can also be expensive to implement. It's worth considering if using these techniques is necessary for your specific use case. If your application stores recent patient health records, that's super important data that needs to be protected. You want to apply the most stringent security practices. But if you're dealing with patient health records from the 1800s, you'll need less comprehensive security measures, since this data is much less sensitive given its age. There's a bunch of other reasons why you might have doubts about cloud providers. For example, you might be wary of where your data is going to be stored. Or you might fear that the support offered won't satisfy your needs. No matter the reason, it's important that you carefully read the terms of service to understand the conditions and figure out if the service offered will satisfy your needs. You know, in a way, cloud services are a little like actual clouds. They come in all different shapes and sizes, and sometimes a dark, stormy one comes along to rain on your productive day. But if you prepare in advance with the right security measures, and maybe an umbrella, working in the cloud will be nothing but a breeze. A lot of companies today are looking into migrating at least part of their IT infrastructure to the cloud. The details of the migration will depend on what your infrastructure currently looks like, and what you're trying to achieve by migrating to a cloud provider. In general, we're looking at a trade-off between how much control we have over the computers providing the services, and how much work we need to do to maintain them. We've called out that when we use infrastructure as a service, or IaaS, we deploy our services using virtual machines running on the cloud provider's infrastructure. We have a lot of control over how the infrastructure is designed, which can be super useful. For example, we can decide which of the many available machine types to use, and what kind of storage to attach to them. IaaS is especially useful to administrators using a lift and shift strategy. So what does that mean? Say you work at a small organization that's expanding. As the company grows, physical space for employees, desks, ping pong tables, and printers becomes scarce. Eventually, the whole office might need to move to a larger space. This means moving not just the desks and printers, but also any servers running on-premise. If physical servers need to be moved, you might need to take a server from the old office, turn it off during a maintenance window, load it onto a truck, and physically drive it to the new location. This could be the new office, or maybe even a small data center. So you're literally lifting the server and moving it to a new location. That's where the lift in lift and shift comes from. When migrating to the cloud, the process is somewhat similar. But instead of moving the physical server in the back of a truck, you migrate your physical servers running on-premise to a virtual machine running in the cloud. In this case, you're shifting from one way of running your servers to another. The key thing to note with both approaches is that the server's core configurations stay the same. It's the same software that needs to be installed on the machine to provide its functionality, no matter if the server is hosted physically on-site or virtually in the cloud. If you've already been using configuration management to deploy and configure your physical servers, moving to a cloud setup can be pretty easy. You just have to apply the same configuration to the VMs that are running in the cloud, and you'll have replicated the setup. On the flip side, Using this strategy means that you still have to install and configure the applications yourself. You need to make sure that both the OS and the software stay up to date, that no functionality breaks when they get updated, and a bunch of other things depending on which specific application the server is running. One alternative, in this case, is using Platform as a Service, or PaaS. This is well suited for when you have a specific infrastructure requirement, but you don't want to be involved in the day-to-day management of the platform. In an earlier video, we mentioned the example of an SQL database that could be used in this way. By leaving the management of the database to the cloud provider, you don't need to worry about having the right disks attached to the computer, configuring the database, or any other task related to the machine setup. Instead, you can focus on just using the database. Another example of Platform as a Service are managed web applications. When using this service, you only have to care about writing the code for the web app. You don't need to care about the framework for running it. This can accelerate development because developers don't have to spend time managing the platform and can just focus on writing code. Some popular managed web application platforms include Amazon Elastic Beanstalk, Microsoft App Service, and Google App Engine. While these platforms are very similar, they aren't fully compatible. So migrating from an on-premise framework and switching between vendors will require some code changes. Another related concept that you might have heard of is containers. Containers are applications that are packaged together with their configuration and dependencies. This allows the applications to run in the same way, no matter the environment used to run them. In other words, if you have a container running an application, you can deploy it to your on-premise server, to a cloud provider, or a different cloud provider. Whichever you choose, it will always run in the same way. This makes migrating from one platform to the other super easy. When talking about migrating to the cloud, you may also hear about public clouds, private clouds, hybrid clouds, and multi-clouds. Let's check out what each of these mean. We call public cloud the cloud services provided to you by a third party. It's called public because cloud providers offer services to, you guessed it, the public. A private cloud is when your company owns the services and the rest of your infrastructure, whether that's on-site or in a remote data center. It's private because it's just for your company, like having your own cloud in the sky. A hybrid cloud is a mixture of both public and private clouds. In this scenario, some workloads are run on servers owned by your company, while others are run on servers owned by a third party. The trick to making the most of the hybrid cloud is ensuring that everything is integrated smoothly. This way, you can access, migrate, and manage data seamlessly, no matter where it's hosted. Finally, multi-cloud is a mixture of public and/or private clouds across vendors. For example, a multi-cloud deployment may include servers hosted with Google, Amazon, Microsoft, and on-premise. A hybrid cloud is simply a type of multi-cloud, but the key difference is that multi-clouds will use several vendors, sometimes in addition to on-site services. Using multiple clouds can be expensive, but it gives you extra protection. If one of your providers has a problem, your service can keep running on the infrastructure provided by a different provider. As we've called out, there's a bunch of different cloud providers that you can use for your projects, each with some specific advantages depending on what you're trying to achieve. And while some terms used by one provider might not exactly match the ones used by other providers, the concepts are the same. In these videos, we'll use the Google Cloud Platform to demonstrate our examples, because, well, it's the platform we know best. All cloud providers give you a console that lets you manage the services that you're using. This console includes pointers to a lot of different services that the providers offer. Seeing all of the options available can be a little dizzying at first, so it's a good idea to start just by familiarizing yourself with the platform before you try to do something with it. This can mean, for example, looking at the available menus and options, and figuring out where the sections that let you use infrastructure as a service are located. No matter the exact menu entries, when you want to create a VM running in the cloud, there are a bunch of parameters that you need to set. These parameters are used by the cloud infrastructure to spin up the machine with the settings that we want. You'll start by choosing the name assigned to the instance. This name will later let you identify the instance if you want to connect to it, modify it, or even delete it. You'll also have to choose the region and zone where the instance is running. As we called out in an earlier video, you'll generally want to choose a region that's close to your users so that you provide better performance. Another important option that you'll need to select is the machine type for your VM. Cloud providers allow users to configure the characteristics of their virtual machines to fit their needs. This means selecting how many processing units, or virtual CPUs, and how much memory the virtual machine will be allocated. You might be tempted to select the most powerful VM available. But of course, the more powerful the VM, the more money it will cost to run it. As a sysadmin, you may need to decide between costs and processing power to fit the needs of your organization. When setting up instances like these, it's a good idea to start small and scale as needed. On top of the CPU and memory available, you'll also need to select the boot disk that the VM will use. Each virtual machine running in the cloud has an associated disk that contains the operating system it runs and some extra disk space. When you create the VM, you select both how much space you want to allocate for the virtual disk and what operating system you want the machine to run. To create these resources, we can use the web interface or the command line interface. The web UI can be very useful for quickly inspecting the parameters that we need to set. The UI will let us compare the different options available and even show us an estimation of how much money our selected VM would cost per month. This is great for experimenting, but it doesn't scale well if we need to quickly create a bunch of machines or if we want to automate the creation. In those cases, we'll use the command line interface, which lets us specify what we want once and then use the same parameters many times. Using the command line interface lets us create, modify, and even delete virtual machines from our scripts. This is a great step towards automation, but it doesn't stop there. We can also automate the preparation of the contents of those virtual machines. Imagine spending an afternoon installing and configuring your new web server. You can do this on one machine, and the process is fairly straightforward. You install any necessary software, you modify any configuration settings, and then make sure that it's working correctly. But it would be hard to reproduce this exactly on another machine, and impossible to do it on thousands of machines. This is where reference images and templating come into play. Reference images store the contents of a machine in a reusable format, while templating is the process of capturing all of the system configuration to let us create VMs in a repeatable way. That exact format of the reference image will depend on the vendor, but often the result is a file called a disk image. A disk image is a snapshot of a virtual machine's disk at a given point in time. Good templating software lets you copy an entire virtual machine and use that copy to generate new ones. Depending on the software, the disk image might not be an exact copy of the original machine, because some machine data changes, like the host name and IP address. But it will have the data that we need to make it reusable on lots of virtual machines. This can be super helpful if we want to build a cluster of 10,000 machines, which all have identical software. Up next, we'll do a few demos of this process. We'll show you how we can create new VMs in Google Cloud Console, how we can customize those VMs, and how we can use templating and reference images to automate the creation. Okay, let's get started with creating a virtual machine on our GCP project. We'll kick things off by navigating to console.cloud.google.com, which is where you'll find the Cloud Console for GCP. Here, the first step is to create a project so that our VMs are associated to that project. We need to give our project a name. Let's name it First Cloud Steps. Our project is being created. It takes a couple of seconds. Now that we have a project, our dashboard has a lot more info. Next, we want to go to the menu entry that lets us create virtual machines. To do that, we'll go into the Compute Engine menu and select the VM Instances entry. This screen is pretty empty because we don't have any VMs yet. We can create a VM by pressing the Create button. Here, we're shown the many different options that we can set for this VM that we're creating. We can set the name, the region and zone, the machine type, the boot disk, and so on. We'll start by calling this machine Linux-instance. Now it's time to select the region and zone. If we click on the region dropdown, we can see all the regions that are currently available to create new VMs. If we click on the zone dropdown, we can see the zones available in that region for new VMs. For this example, we'll just keep the default regions, but as we called out, if you're deploying a service, you should select something that's close to your users. Next, we need to select the type of machine that we want to use. We can select between general purpose and memory optimized. And among each of those families, we can select a bunch of different machine types. We can select how much CPU and how much memory we want our VM to have. The right selection will depend on what we plan to do with the computer. For our example, we'll just keep the default machine. After selecting the VM, we need to select the disk that we want to use. The default disk is 10 GB in size and comes with a Debian image on it. We can select a different size or different OS by clicking on the Change button. There's a long list of available operating systems to choose from. The right option will depend on what you're trying to do with your instance. For this example, we'll choose one of the Ubuntu versions. We can select which type of disk we want to use, either the standard disk, which is cheaper, or the SSD version, which is faster. And we could also change the size if we needed extra storage for our server. For now, we'll just keep the default values here. After the boot disk, we're shown options to determine how access to the machine will work. This can be very simple or very complex depending on the rest of your project. The default access option allows you to access the instance remotely using SSH, so we'll go with that one for now. And finally, the creation wizard lets us pre-configure some firewall rules. Selecting one of these two options would let HTTP or HTTPS traffic reach our machine. Of course, there are more firewall rules that you might want to set. Those can be set later on, after the machine is created. In a later video, we'll want to connect to a web server on this machine, so let's turn HTTP on. There are a lot more options we can set, which are tucked away under this link. We won't look into those now, since the defaults make sense for our test machine. But you can check them out on your own to see what other parameters you can set. We're basically ready to create our VM, but before we do that, let's click on the command line link. This will show us how we would create the same VM through the command line. Wow, that's a long command line. But don't worry, you don't need to understand all of those parameters. The takeaway here is that you could select all the options that you want to create the VM that you need, and then copy this command to create a bunch of VMs that are all exactly the same as the one you selected. For now, we'll close this window and then create the VM using the Create button. Our instance is being created. This takes a bit of time. The system is assigning the necessary resources to our machine, deploying the operating system image, connecting the network interfaces, and so on. Once it's done setting up, we can connect to it using SSH. Again, it takes a little while for the system to set up the keys that we'll use to log on. But once it's done, we can use the machine remotely. Let's check that the machine we created is using the OS we selected. And with that, we've just created a VM using the web interface and connected to it using SSH. How cool is that? Once you're logged into the machine, you can treat it like any normal Linux machine, which is pretty awesome. For example, we can get a text version of the weather in our current location by calling the curl command, which we can use to access web pages from the command line, and passing in wttr.in as the website. Looks like it's overcast in the cloud. Up next, we'll start experimenting with our VM by deploying a simple web application to it. In our last video, we checked out how to create a single virtual machine in the cloud. That's cool, but not too useful at cloud scale. Remember, cloud-scale deployments are often comprised of hundreds or thousands of machines, so creating a single server is only the beginning. Let's make some changes to that VM so that we can deploy it at scale. Once we're done, we'll use the instance that we configured as the base for our reference image. Remember that a reference image is just a file or configuration that we can deploy repeatedly and with automated tools. This is important because it lets us build scalable services very quickly. Let's start by logging into the virtual machine we created in the last video. We'll use Git, which will let us clone the repository with the code for the app we want to deploy. The repo we've cloned includes a very simple web serving application written in Python. Let's run it to see what happens. Our script prints a single line saying that it's listening for connections on port 8000. What's happening behind the scenes is that the application is opening a socket and listening for HTTP connections on that port. In this case, it's running on port 8000, and if we were running this locally on our machine, we could connect to that port. But this is running on a virtual machine in the cloud, which has a firewall and only a couple of ports enabled. What are our options? The script actually lets us pass the port number that it will open as a parameter. We want it to run on the HTTP port that we configured in our last video, which is port 80. And because this is a system port, to let our application use it, we'll need to run it with admin privileges. So, let's stop the running process now by pressing Ctrl-C, and then run it again with sudo and pass port 80 as the parameter. Stop. Sudo 80. Now we can visit the website served by our VM and see its contents. Let's navigate to it. Our web app is extra simple. It just prints Hello Cloud to the web page generated when we make a request. It also prints the hostname and IP address of the machine. This will help us later on when we deploy the solution at scale. Alright, we have a web serving application running on the HTTP port. That's nice, but we had to start the application manually, so this doesn't scale. To get our application to start automatically, we need to configure this as a service. Fortunately, our repo already includes a service definition that we can use. Let's check out the contents of that file. This is a systemd file, which is the initializing system used by most modern Linux distributions. Don't worry if you don't understand what's going on here. You don't need to understand the details of this file to know how to deploy services to the cloud. Just notice that the configuration expects the script that we want to execute to be in /user local bin. We need to copy that file over to there, and then copy the service file to /etc systemd system, which is the directory used for configuring systemd services. And finally, we need to tell the systemctl command that we want to enable this service so that it runs automatically. Okay, now that we've done this, anytime this machine starts, it will start the web app that we've configured, and we'll be able to see the content that we saw before. Let's try it out by triggering a reboot. We've rebooted the machine. This will take a while to complete. It tells us that the connection was lost and that we can ask our terminal to reconnect. This will take a bit of time until the machine has finished rebooting and is ready to receive connections. Patience, my friend. Okay, our VM has rebooted. We can check if our application is running by using the psax command to get a list of the running processes and filter it so we keep only the ones matching a pattern using the grep command. In this case, we'll use hello as the pattern. Yay, our application is now running on startup. We're almost ready to turn our configured VM into a template for creating a lot more of them. But before we do that, we need to think about how we'll upgrade our web app when we want to make changes to it. There's a bunch of different options here. One option is to create a different reference image each time there's a new version of the app. This would mean deleting all the old VMs and creating new ones based on the new image. Another option is to add a configuration management system to the images, so that we can use that to manage any changes after the VM's created. We already know how to manage changes with Puppet. Remember our Puppet Master training from earlier videos? Let's install the Puppet client in this instance so it's ready to use Puppet in the future. Now, when we looked into the Puppet server and client setup, we saw that there was a bunch of steps that we need to run on the client side to have it ready to apply the rules. The repo we cloned includes a script we can run, which will do the initial configuration for us. It will also set the Puppet process to run automatically on boot. Let's run that now. Now, anytime this machine starts, it will serve our website. And if we want to update that website's content, we can do that using our Puppet infrastructure. Nice! Our VM is now ready to be used as a basis for a template, which we can use to create as many instances as we need. Up next, we'll check out how to create the template and how to create instances based on it. In the last few videos, we created a VM and then made sure that it was set up to serve our web app and to stay updated via Puppet. We can now use this VM as a basis for creating an instance template, and then use the template to create a bunch of VMs based on it. Let's do that. To create our reference image, we need to have access to the current virtual disk that's running on the computer. So the first step to create the image is to stop the VM. It takes a while for the machine to shut down cleanly. Once it's finished, we can click on the machine's name to see all its details, and then we can click on the boot disk. These are the details of the disk attached to the VM. We can create a snapshot, which is a full copy of the current state of the disk, or an image, which lets us create a template based on it. Let's click Create Image. We'll call our image webserver-image. Here, the creation wizard shows that we'll be creating the image based on the Linux-instance disk, which is what we want. For this example, we'll leave the rest of the settings with the default values. Okay, let's create our image. This is now creating the image that we'll use for our template. As we called out earlier, the tools will keep most of the contents of the image, but remove things that should be different across VMs. Once it's finished creating, it shows us the list of all images that we can access. As you can see, this is a long list that includes a bunch of stuff along with our image. The other images are public images that we can use to deploy different types of VMs. All right, we're now ready to create our instance template. To do that, we'll go to the Instance Template option, and then click Create New Instance Template. As usual, we're shown a wizard that includes a bunch of different options that we can set. We'll keep most of the defaults and change only a couple of things. We'll name our template webserver-template. We'll change the boot disk to use the image we've created. In this screen, we can see the list of all the available images. By default, the list shows the official operating system images provided by the platform. For our template, we want to use the custom image we've created. And finally, we'll also want to enable HTTP access to the instances created with this template. That's it. We're ready to create our new template. This takes a little bit of time to create. Once it's done, we can create instances based on our images. We'll do it once more from the web interface, and then we'll check out how to do it from the command line. Let's go back to the VM Instances entry, and then click on Create Instance. This time, instead of creating an instance from scratch, we'll use the template we've prepared. We'll name our instance webserver-1. Everything else we'll leave as is. Check out how it says that it will use the base image we selected and that HTTP traffic will be allowed. All right, we've created our second VM based on the template. We didn't have to change any options because all of the values were already pre-selected in the template. And the web app that we want is ready to run without us having to configure anything. Let's check that out. Yes, our application is already running successfully on this machine. This is great, but it's still a bit cumbersome if we want to create 10 VMs like this one. For a batch action like that, it's better to use the command line interface. So let's do that. To interact with Google Cloud, we'll be using the gcloud command. We've already installed the gcloud command on this machine. You'll find pointers on how to install gcloud on different platforms in the next reading. We'll start by running the gcloud init command, which sets up the authentication mechanisms between this computer and Google Cloud. We need to authenticate to the Google Cloud system to be able to use the gcloud command to interact with it. Let's say yes here. This opened a new tab in our browser that we can use to authenticate with our account. Let's follow the process here and authenticate. We're now logged into our cloud account. We can choose which will be our default project. Let's select one here. We've selected the default project. On top of that, the initializing wizard lets us select the default region and zone. It's a good idea to select this, as the commands that we use in the future will use that zone and region if we don't specify a different one. This is a long list. There are a lot of different zones available for our instances. As we called out earlier, when selecting where to run your services, you should go with the one that's closest to you. For this example, we'll just go with Zone 1. Once we've completed this authentication, we can use the gcloud command to operate on our cloud project. We can modify the VMs we've created, create new ones, delete some of the existing ones, and a lot more. For our example, we'll use it to create 5 additional VMs. It goes like this. First, we call gcloud. Then we pass the compute parameter that's used for everything that has to do with virtual machines. Then we pass the instances parameter, as we'll be dealing with the VM instances themselves. So then we pass create, as we want to create instances. We'll say that we want to use the source instance template called webserver-template. And finally, we'll give the name of the instances that we want to deploy. Let's call them WS1, WS2, WS3, WS4, and WS5. It takes only a short while until all instances are created. This is definitely much faster than going through the web interface, and much easier to automate through our scripts. And with that, we've seen how we can create a virtual machine, customize it, create a template out of it, and use that template to create a bunch of new identical virtual machines. Over the past few videos, we've checked out some of the features we can use when running services in the cloud. As we called out before, the biggest advantage of using cloud services is how easily we can scale our services up and down. Now, to make the most out of this advantage, we need to do some preparation. We'll set up our services so that we can easily increase their capacity by adding more nodes to the pool. These nodes could be virtual machines, containers, or even specific applications providing one service. Whenever we have a service with a bunch of different instances serving the same purpose, we'll use a load balancer. A load balancer ensures that each node receives a balanced number of requests. When a request comes in, the load balancer picks a node to serve the response. There's a bunch of different strategies the load balancer uses to select the node. The simplest one is just to give each node one request, called round robin. More complex strategies include always selecting the same node for requests coming from the same origin, selecting the node that's closest to the requester, and selecting the one with the least current load. As we called out, instance groups like these are usually configured to spin up more nodes when there's more demand, and to shut some nodes down when the demand falls. This capability is called autoscaling. It allows the service to increase or reduce capacity as needed, while the service owner only pays for the cost of the machines that are in use at any given time. Since some nodes will shut down when demand is lower, their local disks will also disappear and should be considered ephemeral or short-lived. If you need data persistence, you'll have to create separate storage resources to hold that data and connect that storage to the nodes. That's why the services that we run in the cloud are usually connected to a database, which is also running in the cloud. This database will also be served by multiple nodes behind a load balancer. But this is typically managed by the cloud provider using the platform as a service model. To check out how this works in practice, let's look at an example of a web application with a lot of users. When you connect to a site through the internet, your web browser first retrieves an IP address for the website that you want to visit. This IP address identifies a specific computer, the entry point for the site. Commonly, there will be a bunch of different entry points for a single website. This allows the service to stay up even if one of them fails. On top of that, it's possible to select an entry point that's closer to the user to reduce latency. In a small-scale application, this entry point could be the web server that serves the pages, and that would be it. For large applications where speed and availability matter, there will be a couple of layers in between the entry point and the actual web service. The first layer will be a pool of web caching servers, with a load balancer to distribute the requests among them. One of the most popular applications for this caching is called Varnish, but of course it's not the only one. The Nginx web serving software also includes this caching functionality. And there's a bunch of providers that do web caching as a service, like Cloudflare and Fastly. No matter the software used, the result is basically the same. When a request is made, the caching servers first check if the content is already stored in their memory. If it's there, they respond with the contents. If it's not, they ask their configured backend for the content and then store it so that it's present for future requests. This configured backend is the actual web service that generates the web pages for the site, and it will also normally be a pool of nodes running under a load balancer. To get any necessary data, this service will connect to a database. But because getting data from a database can be slow, there's usually an extra layer of caching specific for the database contents. The most popular applications for this level of caching are Memcached and Redis. As you can see, there's a lot of different nodes in this scheme. Fortunately, once you've done your homework and prepared your setup, you can rely on the capabilities offered by the cloud provider to automatically scale the system up and down as necessary. The infrastructure will take care of adding and removing instances, distributing the load, making sure that each geographical region has the right capacity, and a bunch more things. Up next, we'll talk about some of the things we can do when we need to have more control over the instances that are running our service. Throughout this course and the entire program, we've been talking about automation. As a reminder, automation is the process of replacing a manual step with one that happens automatically. In the past few videos, we've mentioned a few ways that let us automate the creation of cloud instances. We can use templating to create new virtual machines. We can run a command line tool that automatically creates new instances for us. Or we can choose to enable auto-scaling and let the infrastructure tools take care of that depending on the demand. But all of this automatic creation of new instances needs to be coordinated so that the instances correctly interact with each other, and that's where orchestration comes into play. Orchestration is the automated configuration and coordination of complex IT systems and services. In other words, orchestration means automating a lot of different things that need to talk to each other. This will always include a lot of different automated tasks and will generally involve configuring a bunch of different systems. Taking the example of the website infrastructure that we saw in our last video, we've seen how we can automate the creation of each instance in the system. Now, say you wanted to deploy a new copy of the system in a separate data center where you have no instances yet. You'll need to also automate the whole configuration of the system, the different instance types involved, how each instance finds the others, what the internal network looks like, and so on. So how does this work? The key here is that the configuration of the overall system needs to be automatically repeatable. There's a bunch of different tools that we can use to do that. These tools typically don't communicate with the cloud systems through the web interface or the command line. They normally use an application programming interface, or API, that lets us interact with the cloud infrastructure directly from our scripts. We'll talk more about other APIs in a later course. In the case of cloud provider APIs, they typically let you handle the configuration that you want to set directly from your scripts or programs, without having to call a separate command. This combines the power of programming with all of the available cloud resources. The APIs offered by the cloud providers let us perform all the tasks that we mentioned earlier, like creating, modifying, and deleting instances, and also deploying complex configurations for how these instances will talk to each other. All of these actions can also be completed through the web interface or the command line, but doing them from our programs gives us extra flexibility, which can be key when automating complex setups. Say you wanted to deploy a system that combines some services running on a cloud provider and some services running on-premise. This is known as a hybrid cloud setup, where only part of the services are in the cloud. This setup is super common in the industry right now. Orchestration tools can be a pretty useful tool to make sure that both the on-premise services and the cloud services know how to talk to each other and are configured with the right settings. Going back to the website example that we discussed earlier, to make sure the service is running smoothly, we should set up monitoring and alerting. This lets us detect and correct any problems with our service before users even notice. This is a critical piece of infrastructure, but setting it up correctly can take quite some time. By using orchestration tools, we can automate the configuration of any monitoring rules that we need to set, which metrics we want to look for, when we want to be alerted, and so on, and automatically apply these to our complete deployment, no matter which data center the services are running in. This might seem like a super complex task, but fortunately there are tools available to make our lives easier. Back at the beginning of the course, we talked about infrastructure as code. And we called out that storing our infrastructure in a code-like format lets us create repeatable infrastructure. And that using version control for this storage means that we can keep a history of what we've done and easily roll back mistakes. These principles also apply to cloud infrastructure. The way we store it might be a little different depending on the tools that we use, but we'll still be storing this configuration in a code-like format using version control to keep track of the changes. This lets us manage large-scale solutions with a small team. We can very quickly have an idea of what the deployment looks like by looking at the configuration. We can try new things out and roll back if anything goes wrong. We can look at the history of changes to figure out why a specific change was made, and much more. Most cloud providers offer their own tool for managing resources as code. Amazon has CloudFormation, Google has Cloud Deployment Manager, Microsoft has Azure Resource Manager, and OpenStack has Heat orchestration templates. These tools are specific to the cloud provider, which means it can be complex and cumbersome to move to a different provider or combine a cloud deployment with an on-premise deployment. An option that's becoming really popular in the orchestration field is called Terraform. Similar to Puppet, Terraform uses its own domain-specific language, which lets us specify what we want our cloud infrastructure to look like. The cool thing about Terraform is that it knows how to interact with a lot of different cloud providers and automation vendors. So you can write your Terraform rules to deploy something on one cloud provider, and then use very similar rules to deploy the service to a different cloud provider. Terraform uses each cloud provider's API to accomplish this. This keeps you from having to learn a new API when moving to a different cloud provider, and lets you focus on the infrastructure design. We saw in earlier videos how we can have a Puppet rule that specifies that a computer should install a given package, and that the local Puppet agent analyzes the computer and decides which installation mechanism to use depending on the operating system, the specific Linux distro, and so on. A similar thing happens with Terraform. The rules that define the resources, like the VMs or containers to use, will use specific values related to the cloud provider, like selecting which machine type to use or in what region to deploy it. But a lot of the overall configuration is independent of the provider and can be reused if we decide to move our configuration to a different provider or we want to use a hybrid setup. And of course, Terraform isn't the only option. Puppet itself also ships with a bunch of plugins that can be used to interact with the different cloud providers to create and modify the desired cloud infrastructure. Finally, let's spend a moment talking about the contents of the nodes or instances managed by the orchestration tools. When dealing with nodes in the cloud, there are basically two options. Either they're long-lived and their contents need to be periodically updated, or they're short-lived and updates are made by deleting the old instances and deploying new ones. Long-lived instances are typically servers that are not expected to go away, things like your company's internal mail server or internal document sharing servers. We'll manage these instances using a configuration management system like Puppet, which can deploy any necessary changes to the machines while they're running. This keeps them updated to the latest state. On the flip side, short-lived instances come and go very quickly. For these cases, it makes less sense to apply changes while they're running. Instead, we normally apply the configuration that we want the instances to have when they start. And we deploy any future changes by replacing the instances with new ones. We can still use Puppet for the initial setup, but we don't need to run the agent periodically, only at the start.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.